Okay, welcome everybody. Thank you for coming along to Quantum Algorithms for Finding Short Vectors. Glad to see that the title didn't dissuade too many of you. So let's see what we have here. Start off with a quick overview. So first of all, Mark took a little bit of content from me earlier on, asking who does what. So we'll quickly recycle that because it's helpful to know exactly who's in the audience. So who identifies more as a quantum person? Quantum backgrounds? Excellent. Okay, who's more? We've got somebody over there. Who's more cybersecurity? Okay, cool. Would anybody say cryptography in particular? Okay. So hopefully a lot of this is going to be new and interesting then. Very nice. So the gist of cryptography, seeing we've got a few cryptographers, but not too many people are native cryptographers. Generally speaking, we've got the symmetric cryptography, which is kind of like the old stuff, pretty efficient stuff. AES, hashes are based on that, and essentially it's lots of scrambling. It's kind of interesting, but the really juicy, interesting stuff, as far as I'm concerned, is in this public key cryptography. So this is your key exchanges, your digital signature algorithms, and this is all the wacky stuff which, if we wind back 70 or 80 years, nobody really had even sort of conceived that public key cryptography could really exist. How can you share a secret with another individual who doesn't even, you don't even have any kind of exclusive access with? Super wacky. Now, the interesting difference about public key crypto is that it's based on some kind of hard mathematical underlying problem, right? So there's some kind of juicy structure, and when you get into this, you can, stuff gets all super wacky, and we're going to dive into that a little bit later. But basically, breaking cryptosystems reduces down to just solving mathematical problems, right? And that's really exciting bit. Because until this point, mathematicians were really not very useful. Kind of, prime numbers we used for music a little bit, but this really gave us a raison d'etre. So what are we going to do? We're going to try and have a crack at this NP-hard problem, the shortest vector problem. And this is one of the problems which underlies these next generation cryptosystems, which is based on lattices, right? It's a really cool family of cryptosystems. We're going to talk a little bit more about how that's taken off. And it's the hardness of solving this shortest vector problem that makes cryptosystems secure. And the reason I really like talking about and working on the shortest vector problem is because it's really, okay, it's a maths problem, but it's so geometrically beautiful and simple that I can actually explain it to my parents. And whenever anybody, people ask my parents what I do, they say, "Oh, yeah, something like find short distances between points." And it's pretty comprehensible. And then what we're going to do is we're going to try and design a quantum SVP solver, which is, I guess that's the clickbait that got a few of you in here. So the actual structure, being concrete, is despite my maths background, I do not like equations very much. I'm up for ideas and pictures and understanding stuff. And once you understand the ideas and the concepts, the equations are just a way to get to a number or a parameter, right? So not too much dry maths equations, and the ones that are, I try and keep to sort of, v equals x dot b, right? That's about as advanced as that gets, a little bit of linear algebra. I'm going to try and go heavy on nice pictures. Nice pictures are far better for learning. And what we're going to do is we're going to use this, this problem. We've got a crypto system that we want to break. It's based on a mathematical problem, and we're going to create a quantum algorithm to try and see if we can have a crack at solving this problem. And this is a nice framework to basically take us the whole way through a workflow. So we can start off with a brief and high-level intro to quantum computing, because we don't have many quantum native people here. And that's going to be given by Ryder here, who I will introduce momentarily. I'm going to take us through continuous time quantum computing. So this is a really interesting paradigm, which is, it's super different when we actually sort of get into it and describe how it works to the gate model quantum computing, classical computing. But actually it reduces the same stuff, right? Super cool. Then Ryder here is going to give an intro to lattices, the lattice problems, and how it relates to cryptography. And then we're getting to the business end now. How do we take these lattices and how do we map it to something that we can actually put on a continuous time quantum algorithm solver? And at this portion, we are going to move to the interactive part. So if you bought your laptops and you want to participate in this part, then we've got a couple of collabs for you to fill in. You're going to fill in the Hamiltonians. We'll explain what that is later. And hopefully, we're going to be able to submit these queries to the D-Wave 5000Q quantum solver. So if you haven't already got a D-Wave Leap account, it takes 2 minutes to set up, and it will give you an API key. You can just paste that in. And then you just run the whole way through the notebook and just check out your results, and then you can be reasonably confident that we won't be breaking any of these Cryptosystems anytime soon. And then at the end, or for those who don't want to participate in the actual coding part, then we'll do some interactive Q&A because there's loads of questions, loads of interesting discussion topics, and if anything, this from however long I've been studying this workflow, there are far more questions than answers. And we can, there's some interesting other content that we can move on to. So, without further ado, I'm David Joseph. I'm a senior research scientist at Sandbox AQ, and my specialities are quantum algorithms, looking at quantum adversaries. So, what are the capabilities of quantum adversaries against various cryptosystems, and that stuff gets super wacky, very, very theoretical. And I do a bit of theoretical cryptography as well. So, I think NIST have just opened a new group of digital signatures, and a lot of people have been having a bit of fun with that. So I'm on one of the consortia there. That's another topic. You catch me outside of this talk. That gets pretty fun. And my glamorous assistant, which was promised to you in the abstract, is Ryder LiuLin. So over to you.
Hello, everybody. I am Ryder LiuLin. I am an intern at Sandbox, and I've been here for, I think, 9 months now. Really enjoying my time here. Really interesting work. And my background is I have a math BA from UC Berkeley, and there's no real focus when it comes to a BA, but I did some work in cryptography research. More so like classical cryptography, so not any of this quantum stuff. So getting to do this was like a really fun experience. And getting to learn about all these quantum algorithms and stuff like that. So yeah.
And how old are you, Ryder?
Oh yes, I'm 19. All right, so I'm going to give a quick introduction to quantum computing. So this stuff sort of crosses into physics as well, and neither of us are physicists. So we'll try our best to sort of give the high-level overview, but when it comes to specific questions about like how does one go about constructing a physical qubit, unfortunately we're not really the best people to answer those questions, but if there are like any physicists here, then maybe you can ask them. First of all, what is a qubit? So we're going to be approaching this from sort of mathematical perspective. So we can think of a qubit as a point on a block sphere. So this diagram is a block sphere, and it's sort of you can think of a qubit as a vector, right? And so in this case, we have the negative z being like a spin 1, positive z, 0. This is sort of an arbitrary choice. This is just a mathematical representation. So again, these are like arbitrary choices that we're making. But yeah, So how do we manipulate a qubit? So to manipulate a qubit, we perform a unitary operation on it, and we'll go more into what a unitary operation is later on. But sort of the important part to keep in mind is that a qubit is sort of a vector, and it's more continuous than a classical bit is, right? Classical bit is either 0 or 1. Qubit, you've probably heard this, right? Sort of a superposition of multiple states. So then we can also talk about operations on single qubits in the same way we can talk about operations on single bits. So here we have 4 different operations, and these are called the Pauli matrices. So we have the identity, we have that in classical computing as well. We have the bit flip, we have that in classical computing as well. But then we also have the bit phase flip and the phase flip. These we don't really have in classical computing. So yeah, these are 2x2 complex matrices. That's the mathematical way to think of these. We have the identity, we have the X, which is the bit flip, Y, bit phase, and then Z, phase flip. And yeah, combinations of Pauli operators can span every rotation on that sphere that we showed earlier. So it's very common to measure these in like the Z basis, so -1 to 1. And then we can refer to this as 0, 1 via that simple operator there. And then the concept of a qdit, so it's very important, this D here, qdit. This is sort of an interesting problem to solve here. So to create a qdit, which is a d energy level system, we can combine these operators over a set of k qubits. So what we want to do here is essentially combine these qubits into a single qdit. So we can sort of think of qubits as just 0, 1, and then a qdit as 0 to d, right? So it's a digit, right? A generalization of a bit. Another important concept in quantum computing is the idea of entanglement. So the idea is that multiple particle states are inseparable. Mathematically, this is encapsulated by the idea that a system state is a sum that cannot be written as a single product term. And then entanglement is broken by some sort of measurement or interference. This is called decoherence. And then, so here's a small example. So if we have a spin 0 particle that decays into 2 spin 1/2 particles, then we can say maybe we measure one of the spin 1/2 particles and it's spin up along some axis. We keep in mind the conservations of like angular momentum and stuff like that. Can anybody tell me what the other particle spin has to be along that same axis? So yes, I see you pointing down, you're correct. So we have one of the spin 1/2 particles pointing up, so the other one must be pointing down. So this is an example of the decoherence that's because of the measurement or the interference. So this one is a bit of a boring math equation, but it's not super important. This is just sort of an illustration of a 2-qubit state. So yeah, if you measure 1 qubit, you can immediately deduce the state of the other one without observing it. Okay, back to unitary operators, as I mentioned earlier. So they are angle and length preserving operators in a vector space. And remember, qubits we think of as vectors. So in our context, what this means is that because they preserve angle and they preserve length, they're preserving probability. So when we're measuring qubits, there's always this question of probability, right? Like, what's the probability that when measured it's 1, or when measured it's 0, stuff like that. So we always need this probability to sum to 1, obviously, over all the different cases. So that's why we need to have this preserving probability property. Another bit of a boring math equation. This one is Schrodinger's equation. It's actually quite cool. It's a differential equation, but it basically governs the time evolution of the system. And if you hold the h constant, which is the Hamiltonian, which we'll talk about later, if you hold that constant, then the differential equation has the solution at the bottom. And so this is psi of t equals u of t times psi of 0. So u of t, that's the unitary operator. So that is the thing that is telling us the state at the given time. It's telling us psi of t, right? Okay, so now on to qubit construction. So I'm going to talk about 2 different methods of constructing qubits. We're only going to be using one of them in the example because it is frankly much simpler to understand. And there are also some physical considerations that come into why we choose it. So this one is the binary encoded method, and this is maximally space efficient because we are combining qubits into a binary number. So every value has a unique representation, right? It matters what place value each qubit is in. And so this obviously needs high quality qubits, but it's maximally space efficient. We need high quality qubits because if a single bit is flipped, it completely changes the number, right? And yeah, so here we can map the phase flip operators onto these qubits, and then we get integers from -2k to 2k minus 1. That's not like, super important, but again, this is sort of just in words explaining what's going on in this big equation here. The Hamming-Weight method, this is the method that we're going to be using in the example. So this one maybe pay a bit more attention to. It's also much simpler, which is nice. So a qubit operator, or qubit operator, sorry, here is just a simple sum of the qubits. Basically, we are counting the number of qubits in the +1 state, and that's giving us our digit, our qubit. So obviously here there are redundant representations, right? So 1, 0, or 1, -1, 1 is the same as 1, 1, -1, right? They both represent the same thing, but it's more robust. So in this case, in our case, in the real world case, we have poor quality qubits, and we have enough space to justify using the Hamming-Weight method. And so because of this poor quality, we can't really get away with using the binary encoding method because there's just too much risk of like stuff going wrong, going very wrong. Okay, so now I'll pass it back to David Joseph for continuous time quantum computing.
Thank you very much, Ryder. So so in the gate model of quantum computing, in fact, I think actually Quantum Village released an image generator for quantum circuits, right?
A font.
Sorry?
A font.
A font for quantum
Q-type
circuits,
font.
right? Absolutely magical. So basically, you kind of start off somewhere, with the state, and then you run through and you apply a series of gates, and there is some analogous mapping back to classical computing. It's all very dull, but continuous time quantum computing is super weird, right? Because you take these physical systems, and then we just kind of jimmy a problem into it, and we'll talk about it a bit more with the pictures. So I get quite excited about this stuff. So it starts off with what we call AQC, or adiabatic quantum computing, and the crux of it is this one theorem, which is that we have a physical system. It remains in its instantaneous eigenstate. That basically means that whatever its energy level, if it's an electron, it's going to jump or excite or de-excite. If it is evolved under some, Hamiltonian according to the Schrodinger's equation, super slowly, right? So it's like as soon as you try and sort of, move something along too much, it's basically going to put too much energy into the system, and you're going to get some quantum dynamics. But if we move it, really, it's actually pretty much almost infinitely slowly, we can guarantee that that energy state is not going to change. So the corollary of that is that if we initialize this system in the ground state in some kind of easy thing to set up, and then we kind of slowly, sort of gaslight the system into some different Hamiltonian, but we do it so slowly, the system almost doesn't notice. And the thing is, the one that we start off with is a really simple system that that's not so bad to initialize in. For example, the equal superposition of all states. But the one that we finish off in, right, basically represents a solution to some hard problem, right? And if we take this problem and we map it such that the solution we're looking for is the ground energy state, then voila, we've solved our problem. And all we need to do is have quantum systems that can remain coherent for going to the limit of infinity amount of time. So therein lies the problem. Adiabatic quantum computation is great, fancy mathematically, but in the real world, it doesn't quite work so well. However, if we evolve the system much faster than the adiabatic limit, it turns out that we can still kind of get relatively low energy states, right? So it might have excited, but you're still probably talking about pretty low energy eigenstates. Now, if you're looking for an exact solution, then maybe it means that one of your samples probabilistically will be that ground state. You might not have excited. But it's also really good for approximate problems, right? So if you're you don't need an exact solution to something, but you need an approximately low energy state, and this is annealing may be the quantum algorithm for you. So what I just said, this here would be your initial Hamiltonian, which H0 might be equal superposition of all states. HP is this Hamiltonian, which is a system that represents your hard problem. And essentially the way I think about it, we've got a definition of it. It's a function / matrix from one space of physical states to another, and it corresponds to the total energy of the system. And to me, that doesn't mean too much. The way I think about it is we have eigenstates, and eigenstates basically correspond to a configuration of bits, right? We've got a diagram later, but it's just like you read off some bits, and that would be your eigenstate. And each state has an eigenenergy. And that eigenenergy, the lower energy states are going to be the configurations with low energies correspond to the solutions that are really good, right? And to be honest, the schedules that we use to move gradually from the initial Hamiltonian to the final one, you can take a linear schedule where we basically say, okay, we just move the same distance at each time. Then you can kind of muck around with that, and actually turns out the most efficient one is an S shape because of various quantum dynamics that I can talk about later. And I did see a paper recently where somebody had slapped on some deep neural nets to a load of these to optimize the exact shape of the S curve that you need to optimize your adiabatic quantum algorithm. So this is a prime example of lemon squeezing for a physical system that is still absolutely inconceivable from an engineering standpoint. But somebody's already slapped a neural net on it to squeeze out a few extra marginal gains. Quite enjoyed that one. So, the pictures I promised you. This here represents the probability and the energies of the equal superposition. So this is basically the system described by your H0. If you take the state that you've initialized it in and you sample from it, basically it's a uniform random sampling, right? Useless. And eventually what we're going to get to is this probability distribution over all of the states. So basically, this might be like 1, 0, 0, 0, 0, 1, 1, 1, 1, and every state in the Hilbert space that goes along. And essentially what this corresponds to is when you get to this final Hamiltonian, you've got this super localized wave function, and that means when you measure it, there's going to be a super high probability of measuring it in this one, in this state, which is great because it's the lowest energy, right? This is the solution you're looking to get. And what happens is this is done over time, so this is some intermediate time, and it kind of gradually molds like that. So if you think about having so classically, you might have a marble here and you want to get it there. Well, it's not going to happen, is it? With quantum, we talk about quantum tunneling, because you go, probabilistically sort of tunnel through this energy gap. The way I like to think about it in AQC is that you started with the marble here, and then as you slightly perturb it, the marble is always, every time, going to remain at the lowest energy point. And then as you gradually perturb it, that lowest energy point in the overall space is basically going to continuously evolve until it's down here, right? That's the way I like to think about it. So here we go, more diagrams. what happens here is this over here is our initial superposition, so equal superposition, and so the lowest energy state is going to be equal superposition, and these are different energy states here. And you see this ground state. As we evolve over time, the eigenenergies of these intermediate Hamiltonians, they all kind of like squeeze together, and then they open out again for the final problem Hamiltonian, which is when you measure it. What's the time complexity of this algorithm? The time complexity depends solely on how small this energy gap is, right? So if this energy gap gets super, super small, well, basically, how slowly you have to evolve the system for it to be adiabatic and to avoid you basically making this jump depends on the square of this energy gap, right? So you see that's pretty horrible, right? And then, yeah, over here, again, we have our nice marble drawing, right? So here, quantum mechanical tunneling, but you start off and you move it adiabatically and you kind of, like the marble on the sheet. But yeah, so think about this, and this time complexity is really not very nice. And the reason that we don't have good results for this class of quantum computing, right? So Shor's algorithm, Grover's algorithm, they're all in the gate model. In the continuous time model with adiabatic quantum computing, all we have is this bound based on the intermediate Hamiltonian's eigenspectrum. The eigenspectrum literally is, take a slice, what does this look like? And the problem is, it's not at all easy to understand what this intermediate eigenspectrum looks like. We can maybe understand what this eigenspectrum looks like, but this is probably a hard problem for us to understand classically. We definitely know what this one is, but for intermediate problems, very, very different. So the implications are, one, we've got this time complexity gap given by the minimum energy difference, right? So that's a problem. We begin in the ground states, and if we evolve it slowly enough, no jumping. If we evolve it a little bit slowly, but not adiabatic, then we get a little bit of energy jumping, and essentially that means that at the end, we'll get a bit of a Gibbs distribution. You'll notice that if you look at the energy of the things that you sampled from, you'll have basically energy solutions that will kind of be sampled from some kind of Gibbs heat distribution. This model is, even though it looks completely like it's from another world, it is equivalent to the circuit model, and it is universal, the adiabatic version, right? It is polynomially equivalent, which is, I guess, the word mathematicians used to say. I mean, polynomials can be pretty big, but if you're a mathematician, you just kind of just say it. So it's basically, you can solve one problem, then you can solve another problem in a few hours more, basically, which the cryptography is just kind of it's good. And in practice, it requires very long coherence times, right? So, yeah, don't worry about long coherence times with the D-Wave images. So we're going to try it out on the D-Wave quantum annealer. If you've got your laptop and your D-Wave Leap account, right, feel free to set up that account if you want to try this out later. It has 5,000 qubits with an asterisk. So we are not comparing these qubits to the, I don't know, what is it, the Osprey chip records it has, 400 or something?
Yes, Osprey, 427.
427, right? D-Wave and IBM use the same word, the same 5 or 6 letters. There is really very little equivalence between the two. In fact, almost the notion of a qubit in an actual physical sense, or so many dozens of technologies, that is pretty crazy. So that's a whole different debate. There's lots of couplers, apparently 35,000 of them, and each qubit is connected to 15 other qubits, right? So you can entangle a qubit directly with 15 other ones, but you're not going to entangle every one of those 5,000 qubits with every other one of those 5,000 qubits, which is ideally what we'd like to be able to do, because secrets, the magic source of quantum algorithms is entanglement, right? If there's no entanglement, you're running a classical algorithm. So the more connectivity you can get, the more quantum advantage you're going to set yourself up for. And what does this look like? When I said, so this might actually be a diagram of the Chimera topology, which is from the 2000 cube. And this is a diagram of that qubit. So you see each qubit is connected to like a cluster of other qubits. And then each cluster is connected to a cluster of other qubits. So you may be wondering, well, I've turned up here with my NP hard or whatever hard, fully connected problem. I want everything to be entangled with everything else. What am I going to do with that? Well, fortunately, there are mappings, which takes these 5,000 alleged qubits and it reduces them to a much smaller set. But what happens is you set these qubits to be basically very strongly interacting with other qubits, and you create a qubit chain, right? And by using these chains of qubits, so this is what D-Wave would call a logical qubit. Other people call a logical qubit like an error-corrected qubit, but these are not what I would call error-corrected. So I think the quantum computer community needs to have a sit down and discuss pedagogy and naming. But these qubit chains essentially can be all-to-all connected. So here you can see that qubit 4 and qubit 5 aren't connected, but we can create that in an all-to-all connected way. And the cost of that mapping is roughly quadratic, right? So if you've got 10 actual qubits, then in the problem that you want to solve, then when you map it into this thing, maybe you'll have 100 on that, right? Something like that. So there's a cost to it, but it's doable. And the actual D-Wave SDK has a mapping so that you don't need to worry about that, which is helpful. And so Ryder is going to take us through lattices, which is really exciting. Ryder, we are slightly behind time, so enthusiasm, not too much dwelling.
Okay, so just quickly, why are we bothering with any of this in the first place? Classical cryptography mainly relies on integer factorization or something like it, which is broken by Shor's algorithm. You've probably heard of Shor's algorithm before. It basically uses quantum Fourier transforms to do some crazy stuff, and it basically reduces most integer factorization, etc. problems from super polynomials, so faster than polynomial, down a lot. It's not super important to what we're doing, but I'll just mention this is why we want to bother with any of this in the first place. So instead, lattices, they offer new hard problems, like the closest to shortest vector problems, which we'll talk about later on, to base cryptosystems on. And then what is a lattice? A lattice is just a repeating pattern of points in n-dimensional space, defined by n linearly independent basis vectors. So this is an example of a lattice, this picture right here. So we have a basis, like a regular vector space. So we can call these B1s at the end. And then instead of the vector space being any linear combination of those basis vectors, we instead just take the integer linear combinations of those basis vectors. And that's how we get this repeating pattern right here. And so we can define a lattice vector as v equals x times b. And all lattices, just like other vector spaces, have many bases. And so this is the key right here, these many different bases. We want short bases, we do not want long bases. And we'll talk about why later on. So, shortest vector problem. Find the shortest vector in a lattice. If we're given a basis that is the shortest vector, then that's very easy, it's right there. But if we're given a basis that is made up of multiple very long vectors, then the shortest vector might be some linear combination of those two very long vectors. And the closest vector problem is sort of the same as the shortest vector problem. The closest vector problem is just given some point in Rn, so not on the lattice, but just somewhere in the real vector space, find the closest lattice point to it. So we can see right here that blue star right there might be that point that we're given, and then the green circle is maybe the error that we're willing to accept. So the red dot in the second photo is the closest vector. That's the ideal. That's the best solution. But the green vector, the green points inside that circle are vectors that are maybe close enough. Yeah, polynomially close enough. So as David was saying about how adiabatic quantum computing is good for getting maybe very close to the right solution. This is the same thing. We're getting close to the right solution. Maybe we're not actually getting the right solution, but it's good enough. So learning with errors, this is what LWE stands for. Learning with errors is it's the next step up from the shortest vector or closest vector problem to building a full crypto system based on lattices. So the idea is that we are hiding a secret with some noise, some error, E. The equation for that would just be A times the secret plus the error is some B, and then we can use A and B as public keys and then S as the secret key. And so there's two different versions of the learning with errors problem. There's the search version, which is we want to actually find S given A and B. There's the decision problem, which is distinguishing from the output, or distinguishing from A and then distinguishing just from some random, something, right? And solving learning with errors is a special case of the closest vector problem. And the reason for that is we can see in this diagram right here, this sort of looks like a two-dimensional normal distribution, right? The idea is that if we take some distribution on the error and we apply that to the AS plus E equation, then we'll end up if the closest vector is that thing in the middle at the peak of the distribution, then we'll get a bunch of vectors around that when we sample the error, right? And so that's the sort of green circle on the previous slide. So that blue would be near the middle of that distribution, and then that green circle is that sort of circle in this Gaussian right here. And then here.
Yeah, and so learning with errors is the basis of two of the post-quantum crypto systems that NIST and NASA are standardizing. There are four that they're standardizing. One is Sphinx, which is on my t-shirt. Somebody designed a lovely t-shirt after last year's talk. And then there are two based on learning with errors. But basically, many of the lattice schemes are based on this learning with errors problem, which is essentially, and okay, we could include a slide where we show you how you encrypt a bit using this learning with errors thing. We don't have time for that. But essentially, as Ryder just explained, it is the closest vector problem. So if you can find close vectors, then please write a letter to NIST and explain all of your workings, and they'll remove these Cryptosystems from the running. But, there's not much danger of that unless you've already looked into this a little bit. Annealing and encoding in the Ising model. Right, so we've done lattices, right? It's super simple. And if anybody was looking at those diagrams thinking, dude, come on, that looked super easy to find those short vectors. That's because that was in 2 dimensions, right? That is not a cryptographic level of hardness. Usually these are done in sort of high hundreds or low thousands of dimensions. If you're on structure, it gets a little bit different again. But in 2 dimensions, you can visualize what the problem is. It's very geometric. It's very simple. And now we need to work out how we take that and we put it into this this diagram of we start with a marble, move the table clock, and then we end up in some kind of low energy state, which corresponds to a vector which is in that little circle that Ryder just explained. So, okay, yeah, we're still rattling through.
Okay, so quickly talking about what the Ising model is. Originally, it was for modeling ferromagnetism in materials. That's not at all what we're using it for here. So in this case, in this equation here, sorry, another boring equation, but in this equation here, the J's are the terms, the interaction terms between qubits, which is the part that's introducing the entanglement. And the S's are the spins, and then the H is just the on-site energy term for that particular qubit. And we are encoding the shortest vector problem. So in our example, we're going to be encoding the shortest vector problem into the Ising model as QUBO. Again, it's not super important what QUBO means, it's just a type of optimization problem for exploitation. And so when we talk about encoding, we need to talk about the Hamiltonians, right? What are our choices of Hamiltonian going to be? So the initial Hamiltonian is just going to be induced by poly X operators, which are the bit flip operators, if you remember. So those are just denoted by the sigmas here. And this relaxes the system to begin with and is responsible for the exploration part. And this acts perpendicular to the Z basis problem Hamiltonian. Not super important what that means, but yeah.
So, what you see here is a representation of a vector's length, right? Because when we have a basis and we're told, okay, you find a combination of these basis vectors, that will be given basically a series of long chopsticks in n-dimensional space, and you need to combine the chopsticks to find a short vector, right? And how long is the vector that we're going to end up with, right? So these xi's are the combinations, right? So I'll have 5 of that first basis vector, please, and -3 of the second one, and you pick your combination, and at the end you end up with a vector length, which is this the length of v. Now we can actually write the square of that vector length like this, right? This is basically just saying v equals x dot b, right? You take the 2 norm of that and square it, right? So this is just Pythagoras. It's really nothing more than Pythagoras. And if you write that out and you do the you expand all the terms, it's just this. Now, what does this look like when we turn this into our Ising model, right? This is key. Not slide. So essentially, we can think of this as this x as being the output of our QDICs, right? So we're going to put in the basis, that's the input, right? That describes our lattice. And what we want to read off of the quantum algorithm, we want to read off like, okay, what is the combination of the basis vectors? So what is this vector x? So we get given b, we want to work out what x gives us a short v, right? And so these x are what we want to output. And what that looks like is, okay, let's say that we've got a grid of qubits. This grid over here, as Ryder was saying, like you can construct your qubits any way that you want. If we do the Hamming version, where we just sum them up, then maybe this would be like 3, right? If we do the binary version, then 1101 is 13, right? So it's up to you how you construct your QDICs, and there are reasons why you might pick them one way. But essentially, this is your x, right? So x1 times b1, right? So we'll have 13 of basis vector 1, we'll have 5 of basis vector 2, and so on and so forth, right? And so this is what this looks like classically. Now, we just need to take these xi's and turn them into QDIC operators. That's all we do, super simple. Voila, right? Oh, and also the bi dot bj, right? Again, this is just like take a basis vector, dot product it with the other basis vector. And what this is basically you take the whole basis as a matrix. So you do line up the basis vectors in its matrix. You multiply it with its transpose, and it gives you another matrix called the Gram matrix, right? It's basically like a matrix of overlaps, right? It's super simple. It's just take the basis, matrix multiply it with its transpose, and you get this. So basically, you've got a qubit operator times another qubit operator with this Gram coefficient, and that is our problem Hamiltonian, right? So as Ryder just explained, the initial Hamiltonian we might use is Pauli X operators on everything, right? We call this a relaxing Hamiltonian. I quite like that term because basically, it relaxes the system and explores the space. This Hamiltonian localizes the wave function. So if you go on to fit things like the QAOA algorithm, which is where you apply them one, then the other, then one, then the other, it's kind of like you relax the system a bit, you localize it a bit. Relax the system a bit, you localize it a bit. Again, we can talk about that later. QAOA is another thing where we don't know whether it's going to be fantastic or not, but there's some great debates to be had there too. So, what we're going to do now is build the DIY quantum aperture. So, if you're interested in this part, we have some notebooks. I've shortened the URLs. If people would feel more comfortable to see me open these short URLs, I will do it, but I promise you that they're safe. And let me know if they don't work. So you need a D-Wave leap count, which will give you basically an API key, which will be useful if you want to actually see what you're getting back from D-Wave. This is the fill in the blanks Colab, and this is going to be the answers, right? So we're basically going to build this Hamiltonian that we just described. Then we're going to go through, we're going to sort of see what the bit strings we get back from D-Wave are, and then we've got a post-process them, and then we're going to understand exactly what those bit strings actually mean, right? So you get a bit string. Okay, first of all, we're going to turn that into the qubits, right? Which, remember, the Hamming version, we basically just sum them up and divide by 2. So that's what the x vector is. And then we're going to check that the eigenenergies that D-Wave gave us correspond to taking that vector, the x vector, and multiplying it with the basis. And then we can basically see what kind of eigenenergies we get. And then you can play around with the parameters on D-Wave and basically figure out, try putting in a really long coherence time, see if it makes your algorithm work much better. Hint, it doesn't, because there's a lot more engineering to be done on that side of things. But the 5,000 qubit is much better than the 2,000 qubit in my experience. And if you have not bought your laptop or you don't want to do that, then I'd like to invite people to kind of just ask some questions or try a bit of interactive discussion. And then people who do want to try this, just kind of crack on with it and put your hands up and we'll come over and explain.
Just keep in mind when you have your D-Wave leap account, you have a limited amount of time on the processor. So don't try like a crazy coherence time or something like that. Just be mindful of that, and you can check the amount of time you have left on the website. But just running through the notebook once with all the right answers, I think usually only uses about like 0.15% of the computing time. So you don't have to worry about it too much, but just keep it in mind. Yeah.
Oh, and also because we've got the answers here, if you are lazy or not good at maths, then you can also just kind of run through it and just play around with the D-Wave stuff anyway, and you don't have to bother with sort of the Pythagoras stuff and the linear algebra. And then what I'm going to do is, in sort of about half an hour, if people are interested, we've got to talk about other approaches, some adjacent topics, which kind of you can take different directions in. So we'll revisit the slides, but let's go with that. Put your hands up, ask questions, get stuck in.
So what exactly is D?
Ooh, what exactly is D energy? Let's go back. So a qubit would look like, picture a qubit which has values between 0 and 15, right? So this would be 4 qubits, which are constructed. And let's say that their eigenenergies are the integer value, right? So 0 has eigenenergy 0, 1 has eigenenergy 1, etc., etc. Basically, that would be a problem Hamiltonian on a 4-qubit system, which would basically say 0, 0, 0, 0 gives this energy level, and 0, 1 gives this, 0, 0, 0, 1 gives this energy level, and so on and so forth. So basically, it's just an ordering of energies based on the readout. And there are physical systems which can be natively D level, D energy level, right? That's pretty interesting. But for most of the quantum computing systems that we look at today, we construct them out of 2-level systems. So if you want to make your own qubits, you've got to basically define some mapping yourself. I'll go gentleman at the back first.
But now that you're in that slide, you're talking about complexities. Depends on the wave, the size of the wave that you have right there. When you mentioned the next slide, you said polynomial lower bound, or did that mean the next one? Yeah, you said there's polynomial that you can solve. That's a complexity, right? Lower bound. What would be the optimum of that? Depends on the wave.
Okay, interesting. So, first of all, people doing the collabs. Because I've changed the slides. Does everybody who wants to take a look at the collabs have the links? Okay, good stuff. So
you might want to mention that it's a capital L, it's lowercase l at the beginning, and a capital I at the end.
lowercase
Lowercase l and then capital I. This guy figured it out.
Thank you for mentioning that. Did everybody hear that?
Say it again. I pointed out on the slide.
Yeah. Lowercase l at the beginning and capital I at the end. Yeah.
How can you not see that?
It's clearly obvious to everyone.
To everyone with computer vision, the AI is way ahead.
So I was gatekeeping the collabs there. I only want people with initiative taking part in this exercise. Thank you for that. So, what I mean here is, when I say polynomial equivalent, I mean you could take Shor's algorithm and you could map it into an adiabatic quantum computer. Don't know why you would, but you could. And what it means is that however long it's going to take you to factor that integer, it's only going to take you polynomially longer or shorter, right? But basically roughly the same time to a mathematician, right? Not to you or I, but to a mathematician, it's going to take roughly the same time. And the reason it's going to take roughly the same time is because this gap is going to be roughly the same as whatever that would be in the gate model, right? If it's polynomially longer or polynomially shorter, but we only really care when stuff gets exponentially longer or shorter. Yeah, you next.
Could you describe again the connection between tunneling and the continuous time annealing? Is the idea that with annealing and continuous time, the ball stays at that lowest point and it evolves like that, and so it stays lowest, and then but if you were to look at it from the tunneling perspective, it's like it moved from one to the other through the higher energy state. Is that the right way to look at it?
That's a very good question, because now that I think about it, it was a little while ago that I did this work. It's actually slightly fuzzy to me, so if anybody feels authoritatively that they have a better answer, then step in. But the way that I would think about it is that in the AQC version, you start off with the marble on the flat table block, and you don't really need to tunnel through any of these walls, because it always remains at the instantaneous lowest level. That may be incorrect, but that's what I think the answer is. However, for example, if you do the quantum optimization algorithm, where you localize the Hamiltonian a bit, and then you relax it a bit, and then you localize it a bit, and you relax it a bit, every time you apply the relaxation operator, you're inducing some level of quantum tunneling between the states. And every time you apply the localization operator, you're basically making the wave function go a little bit more spiky.
And are those two kind of different ways of viewing that transformation of that evolution?
I hope so. This is something where somebody who is much better at the quantum mechanics side of things would come in very handy. And I do not claim to be that person. Maybe I once was. We'll go to that gentleman at the back. Sorry? Oh yes, we have an answer.
Yeah. Pretty much exactly it. The data got theory of quantum mechanics. That your said that you store your system in energy and you'll have some finite number of and you very slowly vary very slowly define based on that path. Why that finite very slowly vary the Hamiltonian, so then you will stay to within a very united factor in that. So the idea is when you have your flat table, we can very quickly say this is the low center of the table first. And then when it's low plane up to the Hamiltonian, by the data theorem, you're going to stay at that low speed.
And then so then to close the loop on that, if you go too quickly, then it's like the ball doesn't stay at that lowest point. It's like it might move up and somewhere else. And then when it evolves, when the Hamiltonian evolves fully, it's not so lowest point, it's somewhere to an error.
And you might end up localizing.
So for the recording, a gentleman who claimed to be an expert in quantum mechanics said that I was close enough to write. And then there was a small amount of discussion beyond that. Any other questions? How do you do the relaxation? Ooh, good question. So, let's go back to these Pauli operators. So basically, if you've got a qubit and you apply, so what we do is, the problem Hamiltonian, we generally, in the transverse Ising model, the transverse is what we mean by like we have a transverse field, is the problem Hamiltonian is induced by basically a load of z's, right? And anybody who's going through the Colabs right now will notice that the Hamiltonian is all implemented in terms of z's. When Ryder showed us how we constructed the qubits, we constructed them out of z-gates, and that basically gives us a nice 1, -1 reading off. This bit flip operator is basically like saying, I guess one way of thinking it is, like, yeah, it's bit flip. It's kind of saying like, okay, whatever, wherever you think you are, we're just going to like mix things up. We'll explore a little bit more. We'll, like relax. You might not have the right answer yet. And the way you can think of this is, you've got or the way I think of it is that you've got your problem Hamiltonian doing its thing, and then you you have this relaxing field which kind of comes perpendicular, and I don't know why that would make sense, but I always found that helped me. Just think of like something's happening in this plane, and then you just kind of have like some relaxing field coming from up above. Kind of smooths everything else a little bit, and then it carries on like that. Yeah, you look perplexed, but I mean, we'll find coping strategies for getting through long periods of work in quantum computing or quantum mechanics, and yeah, it's a notoriously counterintuitive subject, so don't worry too much about that. Just follow the Colab, and yeah, I promise it works.
Could you, in the slide that you had that was describing the mapping onto the correct word?
The binary one?
Yeah. When you showed the matrix of the bees,
The matrix of the bees.
and you said that
Say when?
I'm hearing encoding. Maybe
I'm going the wrong way.
I think you're right. Encoding. Or to the end. Oh no, sorry.
I
No.
was talking about the one in the diagram.
The diagram of qubits. Okay.
Yeah, qubits. Yeah. When you you say that the right form for the x's is
Yes.
the output of a qubit function over the p's. Yeah, this is
Got it.
Why is or the next slide? One after that. Sorry. Why is that the right form for the x's?
Why is this the right form for the axis?
Yeah, you mentioned like it's either one of two different like encodings.
Right. Okay. So
I just
why would you
missed that.
choose the Hamming version or the binary version?
Or yeah, why is either of them the right form for the x?
Okay. So you can basically, this is like a bring your own qubit mapping kind of thing. It's like there's the one hot encoding, which is super inefficient. There is this binary thing, which is where like each individual configuration corresponds to a different energy level, so corresponds to a different eigenstate. And the reason that you might like this is because people talk about us not having very many qubits, so maybe you think, oh well, we want to be super efficient with the qubits that we've got. We want one configuration to correspond to one qubit, right? Sorry, to one eigenstate. The reason that when I initially did this work, I submitted this to the 2000Q, which was much worse than the 5000Q, and what I got back was essentially garbage. And I was on the verge of giving up on this work, and then my collaborator said, hey man, why don't we just try adding them all up, or just doing this really dumb thing where we just add up all the qubits and we call that the qubit. And I did that, and all of a sudden the result was much better. Now, this is why, right? So it requires many more qubits, but it's more robust. And the reason why is because when you have this where was it? Right, so when you've got this 2 to the p plus 1 term, basically you're saying that the most significant qubit in your qubit is going to have a much stronger interaction with every other qubit, right? And the least significant qubits, when you entangle it, is going to have a much lower interaction. Now, the way the D-Wave quantum annealer works is that you have to squeeze all of your, you get a certain energy budget for how strongly everything can interact. So basically they say, scale everything down to between 0 and 1, right? So you can have your qubit 1 interact with qubit 2 with strength 1 or 5 or whatever. But if you've got a D-level energy system, then basically you've got to scale down 0 to 15 down to this, down to between 0 and 1, so you've got 16 things. But at the bottom, everything is like, the bottom half of that spectrum is occupied by like all but the top row of qubits. So so any noise just massively screws everything up. Whereas with the Hamming encoded ones, everything has like the same strength. It's very egalitarian, right? Every qubit interacts with every other qubit with the same strength, and then it's kind of moderated by the Gram coefficients. But basically what it means is that the lowest energy qubits, the least significant qubits get subsumed by noise. And the reason this is a big problem with SPP is because when I showed you that equation, which is like v squared equals x of b, it's super unstable, right? And what that means is that if x changes by a single bit, right? So a single one of those coefficients changes, then basically you're adding on another really long basis vector onto your combination, which will short. So any perturbation to the the solution that gives you the correct the lowest energy vector, the shortest vector, any perturbation or bit flip is going to give you a really long vector. So it's super sensitive to noise, and it's probably easier to see this. But basically, this is a lot less efficient because it uses more qubits. At least in D-Wave, you kind of have loads of qubits. They're not very good, but it's a form of error correction, I guess. So nothing makes it the right qubit mapping to try. But basically, try it yourself. And then obviously with the gate model, you have error correcting codes. And I think Google recently demonstrated, and quantum, correct me if I'm wrong, and they recently demonstrated that an error-corrected qubit did better in practice than the qubits that weren't error-corrected.
So going back to your question, if you go back to the encoding part, what you depict with that matrix, there were just states of energy that you just captured in that moment. If you go back to the encoding part, because the order is basically only that represent the state. That vector, it can be huge in terms of zeros and ones.
Yeah.
But only depicts that particular capture that you got, right?
Yeah. Once you've read off
Yeah.
so once you've measured the state at the end,
Right.
the wave function has collapsed. You just get a configuration, and that configuration just corresponds to a single vector. Once you have extracted, like, okay, we take our zeros and ones, we turn that into what x is, we matrix multiply to get the vector, and then we take the Euclidean length squared. So that just corresponds, after you've read it off, to a single vector. But up until that point, it's a superposition over a couple of different ones that you can sample with different probabilities. Okay, I will go to the gentleman, but first I want to ask, is anybody going through with the Colab having any sort of major issues, or is anybody finding it okay, or? Yeah, you can get the link to the answers one again. TD Docs 5. And that's less ambiguous, isn't it? The initial Hamiltonian construction is slightly more difficult. The post-processing, so feel free to just copy that across. The post-processing bit's a little bit more broken down, a little bit more intuitive. Actually, Ryder, do you want to just go around and just kind of like on the Colab? Oh, great. Sorry, I was going to this gentleman first, and then I'll come across to you.
So I have a question. The practice. So when you use your
Right.
You have a forward sequence, forward some classical way they're going.
So I'm not catching your question there. Appears to be a bit of commotion in the
Wait a
corridor.
minute.
Okay, the yelling has died down. Could you also speak up a little bit?
Yeah, sorry. So will you repeat that question? So I'm talking, just asking about the short order algorithm, practical standpoint, performance. Because when you have for the model time, and then you have to rely on classical sequencing for work. So have you tried it? What do you use?
So when you say what do you use to share the secrets, I'm still not.
Like when you encrypt the thing, you will have to share the secrets in a classical way. You sequencing for word and you write an algorithm, so you're sure there's no manual error. So you still have to use an algorithm, classical way to share that.
Okay, so in general, so if you take Shor's algorithm, that breaks all of the current breaks elliptic curve stuff, RSA, if you know.
Yeah.
Let's take RSA. So if you're asking about man-in-the-middle attacks, you would do key exchange with RSA, right? But how do you know that you've exchanged your keys with the right person?
Correct.
Right.
But
So then, so in public key cryptography, you would always pair that with authentication, so a digital signature. So, for example, every time you log on to, every time you use the internet, you'll do a TLS handshake, and during that handshake, you will 1, exchange your session keys, and you will 2, authenticate the server, and you can also do that via RSA signatures, right? So it's the same mechanism. And some families of cryptography are good for signatures, but not key exchange and the other way around. But you should always do both to make sure that you're exchanging with who somebody says they are and get rid of man-in-the-middle attacks.
relies on RSA
At the moment, we rely on RSA-like algorithms for signatures and key exchange. So both will eventually. However, the interesting thing is, it's interesting if you can break the key exchange in the future because you can read, but to forge somebody's personality, to forge somebody's identity, you need to have your quantum computer forging signatures in real time. So that's another really interesting direction.
Correct. Yeah. My question was to lower the cost of one and take from the SA and kind of have it. Because I believe the less research. I think 2048 you bet you basically break it in 8 hours or something like that. So I was wondering from the experimental standpoint has been to try to learn non-RSA thing to post-quantum secure.
Yeah, so generally anything based on period finding will just be vulnerable, and anything not based on period finding, no, I'm not going to say that. Not anything not based on period finding. Anything based on, for example, these type of problems, for example, we don't yet have any decent looking quantum attacks, and we don't think we will. Right. So that's about the size of it. We don't know for sure that computers won't be able to break this stuff, but we think they will. Oh yes.
So I actually just wanted to make my question, when it comes to what happens if you move the that, so functions go always now it might be that the position is always in state, but it still isn't 0 actually. So what the data diagram said is that for or like for if you do your Hamiltonian modifications on a time scale that is larger than that's slower than the transition time defined by envelope spacing, you'll end up with the superposition will be almost completely in the state that you started. If you define that state by the energy. What happens if you drive your system quickly? That that low energy state that you're starting will start leaking into these other states. So you're going to end up being in a more complex position with the other states. Now, if implies that you have a sort of continuous trade-off, time and number. Because obviously this is all focused, and the actual limit that the data that you're talking about is as you go to so when you have a large finite amount of time, we're just very confident that our state will end up being the correct proposal, and see we're not proven. We do a few tests to make sure that when we run it a few times, you're good. But if you're running on a shorter time system, then what you see is maybe only 50% of the time you're in the right state, and the rest of them. And as your time scale becomes shorter and shorter, more and more of your state is distributed throughout the alternate state, and this will be longer decades. So that's why you have this trade-off and because it falls out when you need to go down. Because otherwise, There's only going to be leak. The question is how much.
For the recording, more subject matter experts contribution, and Mark Carney, sign this gentleman up for next year. And what I will do now, unless there are any more super pressing questions, is I've got just a couple more slides on different directions that you can take, and then after that I'll put the mic down and then just come around, and anybody who's going on at Colab, we can chat about how that's going. Has anybody had any success in running the Answers one full time through or got to results? No. Okay. Well, we can talk about that. So, alternative approaches. You have this. If this is the adiabatic pathway, then you have this quantum approximate optimization algorithm, which is actually a way of implementing the adiabatic quantum algorithm, but on we can actually run this in the gate model, right? Which is really interesting because basically it discretizes the continuous pathway. And so if the adiabatic stuff is smooth, then the QAOA is done in leaps and bounds. And there's an interesting theory which says basically if you do this in infinite number of steps and an infinite number of approximations, it will exactly be the adiabatic algorithm. QAOA is of interest because we can actually run it at super low depth, and some people like NE5 have showed that for some problems there can actually be some really interesting, some potential quantum advantage for super low depth QAOA, right? So literally just doing one problem Hamiltonian, one relaxation Hamiltonian, and then measure. And that would be really interesting because that's pretty low depth. So this is quite promising. So yeah, that's QAOA. And then another thing is that you can, if you know what your search space is, so for example, previously I showed you a grid of like 4 by 3 qubits or whatever. If you know that your solution is somewhere in that 2 to the 12 space, then you can just grow the search over that space. And we do have time bounds for that. It's essentially quadratically faster than brute force searching over the 2 to the 12 search space. And so what you can do is, in that work where we were looking for the shortest vectors, what we did is we wanted to know, well, how many qubits do we need to ensure that at least the shortest vector, we're looking for the exact shortest vector. How many qubits do we need to ensure that at least the shortest vector is in the search space somewhere? Now we managed to prove that and find a bound based on Minkowski's theorem, which again is like some super cool geometrical stuff. And based on that bound, which tells us how many qubits we need to implement the algorithm I've just described, you could just grow the search over, right? And then you get a quadratic speed up on the search space. So, again, that's just kind of slap on Grovers to the search space, but it gives you some kind of time complexity. What you'll find is that implementing the Hamiltonian that I described as a Grover oracle, we've been trying this, and we end up with a lot of gates, so it's not the most practical algorithm, and it actually leads me to believe that maybe these annealers, the way that you can implement the algorithm and don't have to construct enormous circuits of adders and multipliers to basically do all of these operations, you might actually get a little bit of quantum advantage for certain types of problems on annealers or continuous versions faster than the gate models, just because of the amount of actual engineering and gates that you need to reach the results that we want to. And so I just mentioned the proof technique. You can lower bound, you can upper bound how many qubits you want. So this is the thing, right? With continuous time quantum computing, you can bound the search space, but unless you know that minimum energy gap, you're not going to know exactly how long it's going to take. The best thing you can do is bound the size of the search space and then Groverize it. So the time complexity is really, it's a real sticking point for this class of algorithms. If anybody can solve it and find a generalized way to take an initial Hamiltonian, final Hamiltonian, and lower bound the distance between the lowest energy eigenstate and the upper, and the first eigenstate at any point. Please come and tell me before you publish it yourself, and we'll we'll go forward with that together. That's it. So I'll be around, Ryder will be around. So yeah, come up and ask us questions. But I think we're now at coffee time, so you are all released